All right, so now let's turn our attention from exponents to logarithms. And logarithms are really exponents. They're just kind of another way to write them. So back in the day, mathematicians didn't know how to solve the equation y equals 2 to the x. They didn't know how to solve for x. What they did was they made up an inverse for an exponential function, and they called it a logarithm, hence why we just learned about inverses. So let's just kind of take a look at our calculator and see what's actually happening when we use this log button. So I'm going to go to my calculator, and I'm just going to start doing some of these logs. I'm going to do the log of 10 right away. So you see you got the log, and then you have this ln button. We want to use log. So I'm going to hit log of 10, and my parenthesis, enter. I get 1. Okay, well, what if I do log of 100? I get 2. What do you think if I do log of 1,000? I get 3. What about 10,000? 4. So let's write these down. So I got 1, I got 2, I got 3, I got 4. Okay, do we have a guess of what log of 1 over 10 would be? Oh, I bet some of you guessed it, -1. -1. What about the log of 1 over 100? -2. Are we kind of telling what the calculator is doing? Well, where did this 1, 2, 3, and 4 come from, and -1, -2? Well, think about this number. What do I know about 10 and 1? And what do I know about 102? And 1,003? These are all 10 to that power. So really, this guy was 10 to the first power equals 10. 10 to the second power equals 100. 10 to the third power equals 1,000. That seems to make sense, right? So then 10 to the fourth power equals 10,000, so on and so forth. And same thing down here. If I took 10 to the negative first power, I get what? 1/10. Okay, so it's really taking 10 to some power every single time. So is that true for all logs? Well, we call these common logarithms. And we could also write them just like this. So writing log of 10 is the same thing as writing log of 10 base 10 is what we call it. Same thing, writing log of 100 is the same thing as writing log of 100 base 10. And why do we say base? Because in the second one, it's the base of 10 to some exponent, which in this case is 2, equals my 100. So the base is what the base is. What it is equaling is the exponent, and the number of the log is what that ends up equal, like that 10 to the second power equals 100. So it's kind of confusing, but hopefully the more we do, this starts to make sense. So just know if there's no base, we know it's base 10 because it's a common log. So for example, just like we looked here, log of 10 base 10 equals 1 would be written just like this. Log of 100 base 10, well, the base would go here. The 100 would go here. And the exponent is what it's equal to. Okay, so hopefully we're starting to see this a little bit. So why aren't these nice numbers? If I took the log of 5. So let's think about that. If I go the log of 5, I get some decimal. What about the log of 300? 2.47? Well, because think about this. It's really saying, the log of 5 is saying, remember it's an imaginary 10 that we don't see for the base. It's really saying 10 to what power gives me 5? And then this one's saying 10 to what power gives me 300? Well, 10 to some decimal power gives me 5. And that's what I really found, right? Because if I took 10 to the 0.69897, that number right up there, I should get 5. 69897. Boom. I get about exactly 5. Same thing. If I did 10 to this number, I can just hit second and then answer, take my last answer. I should get 300. That's why, because this 300 is saying like 10 to what power is going to give me 300. So I'm going to get some decimal. That's why I got 2.47. So this is about 2.47, and this is about 0.67. So just remember, if they don't show a base number, it's always base 10 for logs. It's always base 10. So, but logarithms can have any base. We can have any base. So for example, this first one I have a base 2. So this is really saying 2 to the third power equals 8. And this one is saying 35 to the 0th power equals 1. And this guy is saying 3 to the -2 power equals, well, guess what? 1/9. Okay, we're starting to see what it looks like. So this is how they rotate. So the logarithmic form, log of b base a equals c. So the a is the base. That's not nice and easy because that's how I read it. Log of b base a. The c, what it equals is the exponent. And then lastly, whatever the log you're doing, that's what it equals after we take the base to the exponent. Okay, so you just have to get used to seeing it this way. The more you do, the more it's going to start to make sense. So these are the ones I expect us to be able to do mentally. And I bet we could do this first one for sure. So let's think about this. I got log of 16 base 2. Well, if it's base 2, we're saying 2 to what power gives me 16? Well, I could probably think through that one. 2 to the 4th power. Okay, and to check it, this is how you type it in on the calculator. You would say log of 16 base 2. So comma 2 parenthesis. And there we go, 4. And what we'll learn in a little while is we can also write it with division. So this won't make a lot of sense yet, but I could do a log of 16 divided by the log of 2 because it's base 2, and I should get the same thing. Okay, and we'll learn about that property in a little while. But for now, just remember log of the number base whatever it is. And that should give it to us. Okay, so let's try the rest of these mentally here. So I'm saying log of 3 base 9. So base 9. 9 to what power gives me 3? Well, now we're looking at like a root of 9. And 3 would be like the second root of 9. So it's really 9 to the 1/2 power to give me 3. Right? Because it's the second root, which is 3. And I take 3 to the first power to give me 3. So this should equal 1/2. Right? It's the same thing as taking the square root. So now I got log of 4 base 8. So base 8 is going to be set to some power to equal 4. Well, what's an only like root of 8? Well, the only root of 8, a number times itself to give me 8 is 2. Remember, 2 to the third power gives me 8. So right now I know I have 8, and I want the third root. And what do I put on top? If the third root is 2, I have to do what to it to get to 4? I have to square it. So guess where that square goes? On top of the fraction. So remember, I take 3 roots of 8, which is 2, and then I square it to get 4. So this should be 2/3. So that one's, it's a little bit tougher to think through mentally, but hopefully once you do a few of these, you'll start to get it down. So log of 4, base 8, 2/3. Perfect. Right? If you're not totally sure on your decimals, change to a fraction. There we go. All right, last one. Log of base, or so log of 2.25 base 2. So base 2 to some power equals 0.25. I'm going to change this to 1/4 so I could visualize this. Well, I know I need a negative to get the fraction flipped. So I know x is going to be negative. And 2 to what power gives me 4? Well, 2 squared gives me 4. So that one I could probably think through mentally and see that it's -2. And the other way to solve these is to use your common base property. So I could change 1/4 to 2 to the -2 power, and then x would equal -2. That's one way to do it. Same thing up here. I could change 8 to the x to 2 cubed to the x equals 2 squared, and then I could set these guys equal, and I'd get x equals 2/3. So I could use my common base property as well to solve, but hopefully I'm starting to get pretty good at these mentally, and then I don't need to do that. All right, so in order to solve these guys, we want to rewrite them all. So I got log of 25 base x. So base x, and to the second power equals 25, so x would equal 5. Could it be negative 5? Can I take a log to a negative base? Let's try it. Log of 25 base negative 5. Does not work. So you cannot have a negative base. So this is only 5 and not negative 5. So remember, no negative bases, only positive bases. All right, so let's rewrite. So we got 6 to the x power equals 216. And this is maybe where we want to get use our common base property to do this mentally. So 6 to the x equals 6 to the third, so x must equal 3. And now one I could check. Keep going, so we got 2 to the negative 1 power equals x. Well, I just flip it, and it's 2 to the first on the bottom, so x would equal 1/2. So we basically just want to rewrite these as an exponential form instead of logarithmic form. So base 3 to the x power is going to equal the square root of 3. Well, what fraction exponent is the square root? That should be the 1/2 exponent, right? Because it's really the second root, and I'm taking it to the first power. So there we go. Let's just quick look at these on a graph just to set something up. So I got 10 to the x power, and then I'm also going to graph the log of x. Any guess on what these guys might be compared to each other? I zoom standard, so here we go. 10 to the x power is right there, and the log of x is right there. Ooh, guess what? What if I happen to graph my line of reflection for inverses? Think these would be inverses of each other? Oh yeah, there we go, line of reflection. Perfect, so these guys are actually inverses, and I'll quick show you why they're inverses even though we haven't talked to this property yet. So to make it an inverse, I flip-flop, right? So I say x equals 10 to the y power. And to get an exponent, a variable out of the exponent, what happens is I take the log of both sides. And then what happens when I do that, I get log of x equals, when I take the log of this side, it allows me to bring the exponent down in front to be multiplied. So it's really y times the log of 10. So we really haven't explained exactly why that works, but if you really get your logs, it should make sense. And then lastly, to get y by itself, we divide by log of 10. So I'd have y equals the log of x divided by the log of 10. And I did this once earlier, but we didn't explain why it works. I am allowed to write that as y equals the log of x base 10. And if it's base 10, I don't even need it. I don't even need to write it. So that was why it's the inverse. And we will get to that.